Bismillahirrahmanirrahim. Assalamu alaikum, students. Today we will discuss first the heat capacity at constant volume and at constant pressure. So we'll discuss it first. Remember, heat capacity at constant volume we denote as C subscript V, and heat capacity at constant pressure we denote as C subscript P. We have already distinguished these two heat capacities in the last lecture. So when we are heating a system at constant volume, we talk of heat capacity at constant volume. And when we are doing the heating process of a system, keeping the pressure constant, we consider heat capacity at constant pressure. You know that. Now from first law of thermodynamics, we know dq is equal to du plus dw. What is dq? It is the amount of heat added to a system. You know it, I'm just refreshing your memory. So dq is the amount of heat added to a system added to a system. du is change in internal energy, or since it is positive here, it is increase in internal energy of the system, and dw is amount of work done by the system on the surroundings. So you'd also know that first law of thermodynamics is a statement of conservation of energy. So it simply says if you add some heat to a system, this heat will be used by the system partly in increasing its internal energy and partly in doing work on the system. In doing work on the surroundings. Here we are using the convention that positive work is work done by the system on the surroundings, and negative work is the work done by the surroundings on the system. And positive heat means heat put into the system. Negative heat means heat rejected by the system to the surroundings, right? So let me name this equation first. Let us move forward. Now, internal energy U is function of T and V. T is temperature, V is volume. So we can write. So we can write. Use this color. Du can be written as dou u by dou t at constant t dt, sorry, at constant v dt plus dou u by dou v at constant t dv. Just name it equation second. It is simply the differential change in internal energy is written as this sum. What is dou u by dou t at constant v? It is the partial derivative of internal energy with respect to temperature, keeping volume constant. dt is the change, small change in temperature. And dou u by dou v at constant t is the partial derivative of internal energy with respect to volume, keeping temperature fixed. dv is the small change in volume of the system, right? You also know this equation is valid for small changes in internal energy. So just your knowledge of you know it from your previous course thermodynamics, right? So it is dou u by dou t at constant v dt plus dou u by dou v temperature fixed dv. Now I can use it in first here, right? Using equation second in equation first, we get this is our equation first. So I write dq. Now instead of du, I will write this whole expression, that is dou u by dou t at constant volume times dt plus dou u by dou v temperature constant dv. So this whole thing is du, right? Then I have another term which is dw, and this dw now this dw can be written as pdv. Remember, there are two kinds of work. One is called expansion work or PV work. The second is non-expansion work. We assume here that only expansion work is possible. Non-expansion work is not possible, or PV work is only possible. In that case, this dW is written as PdV. So I can write it therefore dou U by dou T at constant V dt plus dou U by dou V at constant T dV plus PD, right? Check it. It's okay. Now what can we do? We can take dV common in these two terms. So we can write dq is equal to dou U by dou T. Let me make it clear. Dou U by dou T at constant V dt plus dou U by dou V at constant T dV we take out plus P times dV, right? So it is first term dou U by dou T at constant V dt. This one dou U by dou T at constant V dt, right? Then we have dou U by dou V at constant T times dV, dou U by dou V at constant T times dV. Then we have PdV. So we have extracted dV out from these two terms, and inside the bracket we have dou U by dou V at constant T plus P, right? So it's okay. Now remember, the defining equation of heat capacity Q is C delta T, where Q is heat put into the system and delta T is the change in temperature of the system, C is the heat capacity. So at constant volume, dV is 0. That means this whole term is 0 because this dV is 0. So at constant volume, I can write dQ by dt, write V subscript here is equal to dou U by dou T at constant V. What is this? It is simply CV. It is heat capacity at constant volume. Subscript V is specifying that volume is constant. We have taken the dt to the denominator of the left hand side. Then we write dq by dt. Subscript V specifies volume is constant. On right hand side we have dou U by dou T at constant V. So we have derived this equation for heat capacity at constant volume. Let me encircle it. and name it as equation 3. This is my equation 3. Now, if you're talking of specific heat, then you take 1 kg of the substance. You take unit mass of the substance, then it becomes specific heat that we have discussed in the last lecture. So equation 3 says that we can obtain the heat capacity at constant volume from the internal energy of the system. We have to simply differentiate the internal energy of the system with respect to temperature in order to get heat capacity at constant volume, right? From experimental point of view, however, it is much more convenient to measure heat capacity or specific heat of a solid at constant pressure than at constant volume. We have another relation which connects heat capacity at constant pressure and heat capacity at constant volume. Let me write that. This is from thermodynamics. We have, I'm writing it directly, but you can look at in your thermodynamics book. We have relation Cp minus Cv is equal to minus T dou V by dou T constant P square times dou P by dou V at constant T. We name it equation 4. If we check it, Cp minus Cv is equal to minus T dou V by dou T constant P square times dou P by dou V at constant T. So we have this relation, and this relation may be rewritten. This may be written in terms of the volume expansion coefficient which is also called expansivity alpha subscript V and the compressibility K defined by let me use some other color. Alpha subscript V is defined as 1 over V times dou V by dou T at constant P, and compressibility is minus 1 over V dou V by dou P at constant T. Alpha V is 1 over V times dou V by dou T at constant P, and K is minus 1 over V dou V by dou P at constant T. Remember, this expansivity is actually what? It is fractional change in volume per unit change in temperature, keeping pressure constant. And isothermal compressibility is the reciprocal of bulk models. You know it. This compressibility is sometimes called isothermal compressibility because we are uh, keeping temperature fixed when we define it. And you need to know also that some books uh, denote or express expansivity by beta, not alpha subscript V. So in thermodynamics book, you will see beta instead of alpha V. In solid state physics, it is represented by many books as alpha subscript V. And one more thing, in some books you may see internal energy expressed as E, not U. So first law, you may see written as dq is equal to dE plus dW. So keep these things in mind, don't get confused. Let us move forward. So when we write this equation 4 in terms of the expansivity and compressibility, or more specifically isothermal compressibility K, it is also in some books uh, specified or denoted by kappa, not K, right? So when we use these definitions of alpha V and K in equation 4, we can write equation 4 as the equation 4 as Cp minus Cv is equal to alpha V square dV by K. Let me encircle it and name it. It is my equation 5. Cp minus Cv is alpha square dV by K. So you can see from equation 5 that Cv may be calculated from Cp measurements if at the same time alpha V and K are known at a temperature of interest. Now, since both alpha V and K are positive quantities, Cp minus Cv is greater than or equal to 0, right? You need to remember it. And let us move to next topic. I should name it the theories of the lattice specific heat. I again want to refresh you that when we talk of specific heat, it is just heat capacity per unit mass. There is one important thing which you need to remember: the vibrational energy, the vibrational energy of a linear chain of n atoms may be expressed as the energy of n harmonic oscillators. This is important. I'm saying the vibrational energy of a linear chain of n atoms may be expressed as the energy of n harmonic oscillators. So if we have a chain of n atoms, we have atom 1, atom 2, atom 3, so on. This way, in a crystal, we have chain of n atoms and they are vibrating at their respective lattice sites. Now they have a vibrational energy. That vibrational energy can be expressed as it is equivalent to the energy of n harmonic oscillators. Now, what is harmonic oscillator? I give you the definition. It is an idealized oscillator which oscillates under the action of a force F equal to minus kx, where x is the displacement of the mass oscillating from the equilibrium position, and k is the constant of proportionality. This equation says that this force is a restoring force. It has tendency to restore the oscillator to equilibrium position because force at equilibrium position is zero. And this force is directly proportional to displacement from the mean position, and it is oppositely directed to it as it is minus here. So if oscillator moves to the right, force acts to restore it to the left, and if it moves to the left, the force acts on it towards right. This is the definition of harmonic oscillator. I repeat, an idealized oscillator which oscillates under the action of this kind of force, F is minus kx. And remember, this oscillator has potential energy of the form this U is here now, potential energy, this oscillator, half kx square. So it will be parabolic when you plot it with respect to position of the oscillator, right? It is proportional to square of the displacement. Force is proportional to displacement, but it is proportional to square of the displacement. So coming back to main thing, that vibrational energy of a linear chain of n atoms may be expressed as the energy of n harmonic oscillators. Now, if we extend the argument to three-dimensional case, then I will write in 3 dimensions the vibrational energy of a crystal containing n atoms is equivalent with the energy of 3n harmonic oscillators. The vibration energy of a crystal containing n atoms is equivalent with the energy of 3n harmonic oscillators. Very important. This 3 comes because there are 3 space directions, x, y, and z, right? Now there are different theories of specific heat for solids, but this feature is common to all theories. And the distinction between the various theories is based on their differences in the proposed frequency spectrum of the oscillators. You need to remember it. The central problem in the theory of specific heat of solids is therefore the calculation of the wavelengths and frequencies of the possible modes of vibration of the crystal under consideration, right? So let us move forward. The classical theory of specific heat of solids and its breakdown. What is classical theory of specific heat of solids and why it breaks down? Let us try to understand it. The energy of a harmonic oscillator, the energy of a harmonic oscillator of natural frequency is one-dimensional harmonic oscillator, more specifically one-dimensional harmonic oscillator. So if its natural frequency is omega, its energy is written as, write it as epsilon p square by 2m plus m omega square x square by 2. It's simple. P is linear momentum of the oscillator. So this is kinetic energy, and this is potential energy. Remember, I said that potential energy of a harmonic oscillator is half kx square, and there's a relation omega square is equal to under root. Sorry, omega square is, there's no under root when we write square. Omega square is k by m. So if you combine these two, you will get potential energy as half m omega square x square. Some books write q instead of x in this expression. So keep it in mind. The energy of a harmonic oscillator of natural frequency omega is written as this: p square by 2m plus m omega square x square over 2. Right? Now there is a classical result called law of, you know it, I am repeating it here, law of Equate, partition of energy. What does it state? It states that for a system of gas molecules in thermal equilibrium at temperature T, the average kinetic energy of a molecule per degree of freedom is half kT, where K is equal to 1.38 into 10 raised power minus 23 joule per Kelvin is for Boltzmann constant. Right? Remember this theorem? At repeated states for a system of gas molecules in thermal equilibrium at temperature T, the average kinetic energy of a molecule per degree of freedom is half kT, where K is Boltzmann constant with this value. Now you need to remember that this law actually applies to any classical system containing in equilibrium a large number of entities of the same kind. Remember it, this law actually applies to any classical system containing in equilibrium a large number of entities of the same kind. Now, why I am specifying this law? When we use this law, the harmonic oscillator in one dimension, it has 2 degrees of freedom in one dimension. One, it can possess kinetic energy. Second, it can possess potential energy. So a harmonic oscillator in one dimension has 2 degrees of freedom. Therefore, on average, it will have energy of half kT corresponding to this degree of freedom and half kT corresponding to potential energy degree of freedom. And when you add up, the average energy becomes kT, right? Let me move to the main topic first, talking of classical theory of specific heat. So we treat these oscillators in a solid as harmonic oscillators. So we can say that average energy of a harmonic oscillator, average energy of a harmonic oscillator, let me write it according to classical statistical mechanics, is that epsilon average equal to kT, right? T is absolute temperature, K is Boltzmann constant. I have told you already that. So if there are n atoms in the crystal, then the energy of the crystal, I will write E, energy of the crystal, which energy? Vibrational energy. Vibrational energy of the crystal, E, is simply 3 nkt. In one dimension, it is just nkt. Because per harmonic oscillator, it is on the average kt. So you have to multiply n. 3 is because of the fact that crystal exists in 3 dimensions. So oscillations are in 3 dimensions, right? Now, if there are 1 mole of atoms in the crystal, then N is Na, which is Avogadro's constant. Then vibrational energy of the crystal E is, you have to simply replace N by Na. It is 3 NaKT. 3 NaKT. And you know NaK is R. You multiply Avogadro's constant by Boltzmann constant, you get R, that is universal gas constant. This is how classical theory establishes the internal energy of a crystal containing 1 mole of atoms. Therefore, heat capacity Cv is, remember, this equation, heat capacity at constant volume. To get that, you have to differentiate the energy, internal energy of the system with temperature. U here is internal energy of the system. Here, in case of solid, this internal energy is the vibrational energy of the crystal, and we have established it using classical theory that it is 3RT if we have 1 mole of atoms in the system. So we have 1 mole of a crystal. So what is Cv then? When you differentiate 3RT with respect to temperature, you will get just 3R. This is simply Dulong petit law, which we have last time discussed. Molar heat capacity of a solid is 3R. Now, according to this classical result, for all solids, molar heat capacity must be 3R, which is not true in practice. That's why this classical theory fails. And another thing, according to it, there is no temperature dependence. Classical theory says that the heat capacity is independent of the temperature, which is not true. In practice, heat capacity at heat capacity varies with temperature. So this is how classical theory breaks down. It doesn't give us the correct picture of heat capacity. Heat capacity varies with temperature. It cannot account for that. Heat capacity is not constant for all solids. It cannot account for that, right? Therefore, there are other theories to account for the things which we observe in practice, and they are not accounted by the classical theory. Those theories we have to discuss in coming lectures. This is all for today. Don't waste your time. Go through all the lectures and do not forget to subscribe and like my channel. Thank you. Assalamu alaikum.